Proof 5.1 proves the product rule. So we start by creating a remainder. Minus f of a, g of a, minus f of a, g of a, minus g of a. Okay, and we want our remainder to have the property that when the limit of the vector h goes to 0, the remainder over the magnitude of the vector h equals 0. And then we also divide our remainder up into 3 remainders. So remainder h equals remainder 1 plus remainder 2 plus remainder 3. Okay, so our first remainder is we make it equal to So in this case, our common factor is function g a plus the increment vector. Okay, and then remainder 2 is equal to f of a h and in this case, our common factor is the function f of a. Our third remainder is equal to minus in this case, our common factor is derivative of f of a. And then what we did in this case is we added in the function g, an a plus the increment vector, times f of a, and g of a plus increment vector of h, and derivative, the directional derivative of f at a. We subtracted it here. Here and here, and then we add it back in here and here. So in the end, we still have the same terms as we have in our original remainder. We have f a plus increment vector h, g plus a increment vector h, and then we have this term here, and then we have this term here, and this last term is here. So it's the same thing. We just added and subtracted in. Okay. Then we can move over here. And so for my first remainder, I want to see that the limit when the increment vector h goes to 0 and r1 of h over magnitude is, which would be equal to, in this case, over, okay, and we know this is equal to 0 because this function is bounded and this is differentiable, so it equals 0, and we've previously proven that the limit of two functions where one is bounded and one is equal to 0, the limit of that is equal to 0. And the same thing happens for the second remainder, except that our common factor is f of a. Oh, sorry. It's like this. It's not equal to. It's just, yeah. It's equal to limit h 0, like this. And instead here we have g, and g. And this would also be differentiable, so it would equal 0. And this is also bounded, so the bounded function times the function going to 0, it would equal 0. In the case of our third remainder, so what would happen is that we would have so this is the unit vector, and we know that this is bounded, and we know that this function is continuous and it's differentiable. So again, due to a bounded function and differentiable function, we know this is equal to 0. And so since all of our three limits for the remainders are 0, we know that in the end, so we have proven that the limit when the increment vector h goes to 0, the remainder over the magnitude goes to 0. Thus we proved the product rule.